So this video is about something called the integrated rate law. Integration is a technique in calculus where we convert the rate law into an equation that relates concentration to time. Okay, so remember that we have done things like plot concentration versus time. And let's just say we have a couple of numbers here. And we're running a chemical reaction, and there's some initial amount. So maybe 1 mole or something else. So we want to think about what's going on here. Well, with 2 points, all we can do is get the average rate, but it doesn't tell us anything about the actual dependence of concentration over time. So no matter what your curve looks like, 2 points is just going to give you a slope. Okay, so let's consider only 3 possibilities. Okay, so put the title, what we're talking about. Okay, so the form was going to be of rate equals K times some concentration to some power, where it's first order, second order, or 0 order. First, and x equals 2, second. And the next thing we're going to do is consider actually a very simple reaction where it's just one reactant on some products. So remember that the rate laws don't depend on the amount of products, but it does depend on the amount of reactants. So we're only looking at one reactant molecule type, and it's either going to be 0 first or second order. Okay, so let's look at maybe a little bit further down the road, 30 seconds. And first thing we can see that this is not a linear graph. Okay, so it turns out we already know it's not 0 order because the integrated rate law is the equation for a line. Okay, so this is not the correct one. Okay, well, the other 2 are not linear. They're kind of curved like this. They start off steep and then slow off. So we need to know what the actual equations are for the first order reaction and the second order reaction. Again, we still don't know. All we know is not linear, so it's not 0. We don't know if it's first or second. And you really can't tell by eyeball either. It turns out that the equation for the first order is natural log. And that the integrated rate law for second order is reciprocal. This is minus KT plus KT. Okay, so you don't know which equation to use until you actually know what order the reaction is. All right, so let's do a problem now. And so let's see, calculate A at 30 seconds. Okay, so we're going to calculate the concentration at this point given a rate constant. Of 0.0170, so I'm going to use 3 significant figures, molar minus 1, second minus 1. All right, now this tells us it's second order from the units. Okay, so this is the equation we're going to have to use. Okay, so if you don't have your order right, you'll be using the wrong equation, you'll get the wrong solution. Okay, so the other thing to realize is that the time zero is kind of arbitrary. Okay, so you can start the reaction at time zero at this molarity, wait 10 seconds, it'll be this molarity. Well, it'd be the same as just starting at this molarity at 0 seconds. So what we're going to do is reset our stopwatch. Okay, at 0 seconds, at the first point, we're going to call it A naught. Right? So A naught is going to be the value at 20 seconds. All right, so let's just plug in the numbers now. This is a very algorithmic approach to solving problems. Very easy for freshmen to do. All right, now the trick with the reciprocals is you want to combine everything to a number as soon as you can so that you don't have fractions. All right, so 1 over A, which of course we don't know. That's the actual thing we're looking for. A naught is the first point is 0.700 molar plus K times T. Well, here's K. Times 20 seconds. All right, so this is going to be 1 over molarity. That's 1 over molarity. Seconds minus 1 times seconds is just going to give us molar minus 1. So everything in this integrated rate law is just going to be, each term is molar minus 1. That way we're combining apples and oranges. Okay, you get out your calculator and you solve this. And the right-hand side, when you take 20 times 0.17, and then plus the reciprocal of 1 over 0.7, you should get 1.769, and that's 1 over A. And then you hit the reciprocal button on your calculator, which is 1 over. So 1 over 1.7 will give you A. And that's answer is 0.565 molar. Okay, so the units of molarity are there, and as they should be. The concentration has gone down, which is what it should be, and it looks reasonable. Okay, so that's how you'd actually work this particular problem. Okay, now most problems I won't have you do this little trick with resetting time to 0, but I just wanted to emphasize that when you start your clock, it does kind of set the scale, and that point should be A naught. Okay. The other thing is that there's an approach where you plot each one of these equations. So if you have some concentrations of A and some times, well, you can take the concentrations and plot them. If you get a line, you know it's 0 order. Okay, we did not get a line. So then we know it's probably first or second. Well, if we were to plot the reciprocals of A, we'll get a straight line. If we plot the logarithms of the concentrations, we will not get a line. All right, so one approach is to do this graphically, or to use a 2-point formula for a line. And so we'll see some examples of that with other types of equations that are mathematically very similar. And that'll be the Arrhenius equation, which is next video.